What's up, midges? Brendan here, and today we'll be continuing with 7 days of Injective, and we will be looking at smart contracts today, right? So for day 2, developing smart contracts, we will go through the full smart contract development process from start to finish. First, we'll clone a starter repo, then install dependencies, then we'll use solc to compile the smart contract source code written in Solidity, and then we'll test the smart contract using programmatic test cases. Then we will deploy the smart contract onto Injective, testnet, and then we'll verify the smart contract on a network explorer. And finally, we'll interact with the smart contract by both reading and writing its state. And that is it. In this first video, we'll be focusing on the first 3, so just the starter repo, and then compiling and testing. And then in a subsequent video, we will look at the rest. All right, what is a smart contract? What exactly is one? At its core, a smart contract is simply a program that runs on a blockchain. Unlike scripts that run on a local machine or on a centralized server, these live in a decentralized network. For EVM, Ethereum Virtual Machine, compatible blockchains like Injective, there are a few languages that we could use: Solidity, Yule, Viper, and a few others. In this series, we will focus on Solidity. It is by far the most dominant language in the space, with the largest ecosystem and tooling support. So this makes it the best place to start. And before we continue, we should also clarify some misleading terminology, because the name itself, smart contract, can be misleading. So let's clarify what it isn't. First of all, it is not smart in the sense of AI or having a brain, etc. It does not think. It is just code that executes the instructions that we give it. And secondly, it is not a contract in the legal sense of the term, right? You can't take a smart contract to a court of law in the same way that you would with a contract that's been written by lawyers. Now, the term smart contract was coined historically to describe the idea of a protocol that facilitates, verifies, enforces the execution of a computer program. And the analogy for this is a vending machine, right? This machine autonomously executes actions according to these predefined and immutable instructions. Immutable meaning it cannot change. If you put money in and press a button, the machine must give you the drink or the snack, right? There's no middleman required. There's no if and buts. There's no arguing, right? And that's the autonomous part of it, right? Now, a smart contract is a computer program that is similar to that, because its code is immutable, because it cannot be changed, because it is stored on a blockchain. So its code is immutable, and therefore we can predict what it will do given any input and its current state. Now, can we do that with a traditional web application that, say, sits on a server? No, we cannot. And the reason for that is because the owner of that server could change the code that is executing behind that server. Can't do that with a blockchain, not with smart contracts. So they are computer programs with decentralized trust. The blockchain enables that decentralized trust. All right, enough theory. Now it's time to get building. So first off, we should open a terminal, and then we'll want to go to the end dates of Injective repo and copy and paste, right? So we want to do git clone and then paste, right? And then we want to cd into in days of Injective, right? So now we're inside that repo. Then we want to navigate into day 2, right? cd day 2. And then within that, we want to go into the smart contract folder, right? So in this folder, you'll see that we have a hard hat project already stored in it. So you'll see over here that we've got a hard hat config file. We've also got the contracts file. So that has got a Solidity file in it. That's our smart contract source code. We've also got a scripts file, right? This will have our deployment logic in it. We also have a test file, which is used to test the smart contract, right? And we don't have an artifacts folder just yet, right? That will come later after compilation. Now, before we begin, we'll need to obtain the private key from the account that we created earlier and save that in the .env file. So I'm going to do copy.env, .example.env to .env. And then all right. So I'm going to open up my repo over here now. And this is where I saved this earlier on. Let's see. Open up day 2 and smart contract and open up the .env file. I'm going to take the private key, which I copied earlier on from when I generated the account, and paste it over here. And then I'm going to leave the testnet RPC URL as is at the moment. Okay, let's do an overview before we start our smart contract developing steps. Right. So this is a sequence that we'll be following. So first, we will write code. So this is writing logic and solidity. Then it is to compile. So we'll use SOLC via Hardhat, which is a developer tool, to turn the code that we've written, which is in a human readable language called Solidity, into machine readable EVM bytecode. Then the next step is to test. So we'll run local tests using Mocha, which is done via Hardhat, to ensure that the logic is correct. Next thing is that we will secure, right? And in this case, we're going to skip it, right? So in a real project, you'll perform a security audit, but for this tutorial, we won't, right? So do not skip the step in production, but for the sake of learning, we'll just skip that because that is a very complex topic in and of itself. Then after that, we're going to do a deployment. So this is to send a transaction that will put our smart contract onto the blockchain. Then we'll verify. So this is publishing our source code to the block explorer so that others can trust it, right? So when you deploy the smart contract to the blockchain, it is just EVM bytecode that's not readable, right? So anyone can see the bytecode, and that bytecode can never change because it's immutable, and that connotes some level of trust. But it is insufficient to fully get trust because you can't see you don't actually understand what that code does. So to have that understanding, that's where verification comes in. And the final step is to interact with it. So we'll use queries to read data from the smart contract and transactions to alter the state of the smart contract. All right. So the next thing is to compile. So let's open up the smart contract that we're about to compile. It's already written, right? And we can see that over here. It's called counter. It has an attribute called value. And there's an increment function which takes in a parameter, which is an unsigned integer. And that value, we do something with it, right? Over here, we'll have a correct implementation that's currently commented up. And we also have a wrong implementation, right? We're going to leave it with the wrong implementation for the moment. All right. So the next thing we're going to do is we're going to do npm I for install, right? And we have installed all the dependencies that were present specified in package.json, namely Hardhat itself, 2 dependencies, as well as .env that allows us to read this file. All right, then we're going to do npx hardhat compile. Okay, so you can see what is done there. It has downloaded Solidity compiler version 0.8.28. That's actually specified over here, right? And then it's also subsequently compiled one file successfully. So recall earlier on that we didn't have the artifacts folder. Well, now we do, right? And what we want to do is we want to take a look inside the contracts, and then you will see a few files here, but the one that you're interested in is under artifacts and then contracts and counter.sol, and you can see counter.json. Yeah, so you can see over here, this is the source name. So that references this file within the project. And then it says, here's the ABI, which is one of the compiler outputs, right? Application binary interface. And the other one that we'll see is the EVM bytecode, right? And this is what actually is stored on the blockchain. Now, let's go into that a bit more detail. So ABI stands for Application Binary Interface, and it is similar to a manual that tells other applications how to talk to your smart contract. It is human readable and a JSON, right? So you can take a look at it here, right? So you can see here that it has a method named increment, and it takes in one parameter of type unsigned integer, and it also has another function over here, and the other function's name is value. So notice that we didn't define a value field here, but we do have a value property, and since it's public, it exposes that function. So we can call a value function, and that will effectively be a getter, right? Yeah. Okay. So the next thing is the EVM bytecode. So let's take a look at that as well. So let's collapse this ABI field and then see this over here. This is not human readable. It's a very, very long string of hexadecimal characters, essentially. So the Ethereum virtual machine can execute this, and that's the point, right? It cannot execute this code, but it can execute this code. Now, the next thing is to run test cases, right? So we already have test cases set up, and do recall in our counter, we have an incorrect implementation at the moment. So when we run the tests, we're expecting them to pass. So before we run the tests, let's take a look at it. So here we go. Close this for a moment. So you can say that smart contract, after being deployed, it'll have an initial value of 0. Then we'll attempt to increment it by 1. And after that, it's supposed to have a value of 100. And after that, we increment it by 23 again. And then it'll have a value of 123, right? So that's our test. And it should pass, but it won't because the implementation is incorrect. So npx hard hat compile. Oh, sorry, not compile. Test. npx hard hat test. All right, so we can see here that these are the test results. Should start with the count of 0, so the first test passed, and then we see here should increment the count starting from 0. This test failed, and it should increment the count starting from a non-zero value, and that test also failed, right? And here we have some additional output, some stats, which we will not get into. But what we will get into is to fix that failure, right? It's actually a good thing that our test failed because it shows that our tests are indeed working. Let's go into the code and fix the logic error that I told you about earlier on. So let's get the correct implementation map and comment out the wrong implementation. So now the source code has changed. We're going to do npx hard hat compile again. So this will recompile, and now we'll have an updated value over here. So this bytecode would have just changed as a result. Not that we'll be able to tell. But when we run the test this time, it is probably going to pass. So npx hard hat test. All right. So we can see here, these are the outcomes, right? So the first test passed as before, and the second and third tests have started passing when they were not passing previously. All right. So that's it. That's how you run a test and fix a bug in the implementation. So let's talk a little bit about what just happened with the implementation and the specification, which comes in the form of a test. So this process touches on something that I called the 4 quadrants of specification and implementation. Ideally, we want a correct specification and correct implementation, right? So that's this over here, right? That's ideal. And a failing test usually, not always, usually means that the specification is correct, but the implementation is incorrect. So that's a true negative. The test is telling us the truth that something is wrong with our implementation, right? Now we have dangerous territory where we have we have this over here, right? And the most insidious one is when we have the wrong specification and the wrong implementation, and that gives us a false positive, right? So this means that you're misled into thinking your logic is okay when actually it is wrong. And that's a little bit more insidious, right? So this is something that I came up with in 2019, and you can go check out the full write-up on it. Link will be provided in the description. All right. Now let's take a look at deploying EVM bytecode, I should say. Right now, that is to be continued in the next video, right? So we have just covered the theory and demos for the first half of day 2 and on smart contracts. And if you haven't gone through the steps yourself yet, please be sure to do so now before continuing to the next video. They'll only take a few minutes to complete. Now, once again, you have the options to rewatch this video from the beginning or follow the text instructions in the linked tutorial. But before you go, note that this is a preview edition of the video that is part of the 7 Days of Injective course. We're creating the full version of this course with all the bells and whistles, and if you watch this far, I'm sure they will be keen on that too. So do sign up using the form by using the QR code or clicking on the link in the description of this video. For now, on to the next video.